In this class, we're going to discuss about TCP congestion control. TCP congestion control, slow start, congestion avoidance, fast recovery, TCP congestion control, retrospective, fairness, fairness and UDP, and fairness and parallel TCP connections. TCP congestion control, additive increase, multiplicative decrease approach. So approach is sender increases the transmission rate. So the window size, so center as and when increase the window size. So probing the for the usable bandwidth until the data loss is occurs. So additive increase means increase the so that is exactly client window by one MSS. So that is exactly one MSS every round trip time. So that is exactly until the data loss is detected. So you keep on increase the window size. So for example, so window size is 3. So keep on increase to the window size is 4 until data loss is occurs. That is accepted by the so window. So that is exactly additive increase. So multiplicative decrease means cut down the client window, C window in off after the data loss. So as and when so the data loss is occurs, so that is a decrease the so window size. That is a client window size. That is what we call as multiplicative decrease. Cut the client window in off. So off, for example, it is a so the window size is 6. If you are increased, cut down into so 3. So that is a n. So n 3 packet at a time. It is a sender has to send. So like that. So here additive increase window size until data loss is occurs. Then cut down in half in the multiplicative. So that is a window size. So that is exactly it is a shown. So here it is a additive increase. So additively increase. So it is increasing. So once it is a cut down, it is off. It is a decreasing. It is exactly it is shown here. It is a decrease automatically. So it is exactly it is shown in AMD sawtooth behavior and probing for bandwidth. So depending upon the bandwidth availability of maximum, so the service of the so that is exactly MSS. So exactly it is the probing the bandwidth is available. It is a TCP congestion we can able to control in this way. So here TCP congestion control details concerned, it is a sending rate roughly send the client window bytes, wait for the one round trip time for the acknowledgement, then send the more bytes of data. Rate, what is the data rate is nothing but so that is a client window size so divided by so one complete round trip time bytes per second. Complete round trip time means sender to receiver, receiver back to sender, that is a one complete round trip time. So in terms of bytes per second. So sender limits transmission, here sender sequence number. So the last byte acknowledged. So this is a yellow green bytes of the packets is a last byte acknowledged. So sent, not yet acknowledgement, that is the yellow. So that is exactly this is exactly so client window, WC window, WND, nothing but client window. Sender limits the transmission, last byte sent and last byte acknowledged. So less than or equal to so the client window. So client window is always dynamic, it is not fixed here. So it is a dynamic is nothing but keep on changing. So that is depending upon that. So that is how many packets you are sending, how many packets you are acknowledging back there. So the client window is defining and function of the perceived so network congestion. Again, it is a TCP slow start. When the congestion is begins, increase the rate. So increase the so data rate exponentially until so the first data loss event has to occur. So initially, what to do for this? So when the congestion is begins, the data congestion is occurs between host A to the host B. So it is increase the rate exponentially until the first data loss event has to occur. Initially, so control window it is a 1 MSS, 1 bytes per second. It is exactly it is sending one. So that is a segment, one segment at a time. So that is exactly you have to send. So one round trip time, so complete round trip time. So one segment reach to host A to the host B. Again, host B to the so one segment has to acknowledge back to the host A from host B to the host A. So one round trip time. Again, two segments at a time you have to send. So again, it is a two segment has to acknowledgement back to the host B to the host B. Again, four at a time, four segment at a time. So that is a double the that is a client window every RTT, one round trip time. So that is a doubling. So one segment, two segment, and four segment. So again, it is also getting the acknowledgement from the server back to the. So that is exactly how testing the window size. Initially, rate is slow, but it ramps up exponentially fast. So that is a TCP slow start. So with a fast. So that is a fast rate. So again, so TCP detecting, reacting to the loss. So data loss indicated by the timeout. So that is a client window set to 1 MSS and window then goes exponentially as in slow start as I explained in the previous window to so that is a so previous slide to threshold then goes linearly. So data loss indicated by three duplicates of development. So it is a data loss. How do you identify? So it is a three acknowledgement is delivered from so server back to that so host. It is indicate that data loss is occurs. TCP reno. It is a duplicate acknowledgement indicates the network capable of delivering the some segment. So duplicate acknowledgement will be getting from the server back to the client. So that is indicate that. So that is a so exactly. So we are indicating that it is a data loss. So the client window is cut in half window then grow linearly. So whatever that, so suppose four at a time it is sending, so three acknowledgement is received. So not so any four acknowledgement. So just three acknowledgement received. So you cut down that so into half window. So that is a multiplicative so approaches to be followed. TCP Tahoe always set the so the client window to one timeout or three duplicates or design as and when timeout before timeout three duplicate acknowledgement is received. So that is a definitely so Tahoe will be followed. TCP Tahoe. So TCP Renault. So it is nothing but so that is a three duplicate acknowledgement. Tahoe always set to so one. So that is exactly cut down the three duplicate acknowledgement as received from the server back to the client. Here, TCP switching from slow start to so that is a CA. You see that so that is exactly so when should exponentially increase switch to the linear. So when the so client window goes to half of its value before timeout. So this is exactly SS threshold TCP Tahoe will follow here. TCP Renault will follow here. So this is exactly it is a close linearly in case of TCP Renault. So TCP Tahoe it is a close. So this is exactly variable SS threshold will be shown. This is the threshold value. So this is limitations. So in a segments, how congestion window it is at segments in terms of segments, eight segments they are defined. Here in case of TCP Renault, so it is a maximum. So six segments is defined here. So it is a exactly it is a linearly grow in case of TCP approaches. So it is a cut down, gets half of its value before timeout. Before timeouts, it is a cut down. So automatically it will be decreased now. Okay. In case of TCP Tahoe, so that is exactly approach. TCP Renault approaches. So it is linearly grows. So threshold will be so limited. Exactly it is will be followed here. Okay. So variable threshold and loss is event is occurs. So that is a so SS thresholds. So is set to half of the so client window just before the so data loss event is occurs. So summary of TCP congestion control as in duplicate is a reacknowledgement slow start. So this is exactly FSM. So congestion avoidance. So that is a fast recovery can also be performed here. So exactly these are the events of so summary of congestion controls, whatever explained in the previous slide. So TCP threshold throughput, average TCP throughput as a function of the window size so per round trip time. So ignore the slow start. Assume always data has to be sent. So window size is measured in terms of bytes. So where data losses occurs, average window size is nothing but number in flight bytes. So is three fourth of so window size. Average throughput is always three fourth of window per one round trip time. So average TCP throughput, how do you calculate? So the always 3 by 4th of window size. So one complete round trip time and bytes per second. This is how TCP throughput. So it is exactly so calculated. So this is exactly shown. So that is a window throughput and it is a so cut down. Half of it is a window throughput It is exactly, it is shown here. So TCP futures, TCP over long fat bytes, example of 1000 bytes of segment. So 100 milliseconds of round trip time. So want 10 giga, so BPS throughput requires W. So throughput 83,333 in-flight segments. So throughput in terms of segment loss probability, so L. So this is according to Mathis in 1977. So TCP throughput has been calculated by Mathis. So 1.22, so multiply by, so what is the maximum segment size has to be sended. So that is one round trip time. So square root of L is calculated to achieve the 10 Mbps throughput. Needed data loss rate of length is equal to 2 into 10 to the power of minus 10. Very small loss rate is expecting new version of TCP for high speed. So TCP fairness. So what is the fairness goal of the TCP transmission control protocol? So if the K TCP sessions share the same bottleneck, so that is a link of bandwidth R. So bandwidth rate is R. Each should have average rate of R divided by, so that is a K TCP sessions. K is here. So how many number of TCP sessions is established? Here in this scenario, TCP connection 1, this is a TCP connection 2. So bottleneck in the router capacity. So router is not able to assign. So for the TCP connection 2, but that is the bottleneck. That is the disadvantages in the router capacity. The router capacity is not sufficient here. That is the bottleneck. So fairness is, so fairness property, what is the average rate that is exactly delivered? So for the TCP connection 1 and TCP connection 2, so that is the average rate it will be delivered. So this is the rate will be average from one router to another routers delivering the packets. Here, why TCP is fair? Two competing sessions, additive increase in the give slope of so one throughput is increases, multiplicative decrease approach is decreasing the throughput proportionally. Additive is nothing but it is so here in this the connection one throughput and connection two throughput has been shown here. So it is exactly the equal bandwidth shared by the, so both approaches, but it is a loss as and when data loss decreases the window by the factor of 2. As you know that congestion avoidance, additive increase. So that is a, so if it is a keep on increasing in the terms of factor of 2. So 2 multiplied by 4, 4 multiplied by, so like that it is keep on increasing. So as and when losses decreases, window by factor of 2, even in the congestion avoidance in the additive increase. So that has been shown here. So that is a equal bandwidth will be shared by both the, so that is a connection 1 and connection 2. So throughput. So fairness and UDP multiplication. So multimedia application often do not use TCP, do not monitor it throttle by the congestion control. So instead of use the UDP protocol, use the datagram protocol, send the audio and multimedia application like audio and video at some constant rate. And because it is a tolerable some extent, so packet loss, some also tolerable some extent. So always expecting the constant rate. Packet loss is a so limited packet loss to be able to tolerate by the multimedia so application. So fairness in the parallel TCP connection, application can open the multiple parallel connection between the two hosts. So web browser do this. Example link rate of with R. So 9 existing connection. New application asks for the 1 and TCP gets at the rate of R divided by, so the rate so divided by 10. New application asks again for the 11 TCPs. So gets R divided by 2. So in this class, we have discussed about TCP congestion control, slow start, so congestion avoidance, fast recovery, TCP congestion control with a perspective, fairness and UDP, fairness and parallel TCP connections.